I think actually after like last my line, but like Claire is my top. And then I told her.
All right, welcome back.
I went to project once, Packers. That doesn't scare me.
That doesn't scare you.
My teacher took that and whacked it on our desk.
Like I've read a lot of
Taylor's afraid of ladybugs, so I didn't want to scare her.
So my teacher would take that and whack it on our desk and we would step out. So we had to step up like this. And you couldn't take it out.
Okay. Yeah. All right. So we're in the final stage of learning all that you're going to need to know for the AP exam on how the derivative can help you figure out what the graph of a function looks like. Okay. And so yesterday we did a brief introduction to concavity. So I'm just going to kind of recap that. And then I'm going to show you a couple of other things, and then we're going to put a summary up. And then we're going to go through, I'm going to try to go through 2 examples, but we'll see if we can get through them. So yesterday we learned that you can describe a function by its concavity. And so we learned these 2 terms, concave up and concave down. Now, we learned a quick visual way to look at it by looking at whether or not it's facing downward, like an upside down bowl, or it's facing upwards here. Okay? So concave up is like the smiley face. Concave down is the angry eyebrows. Okay? And it fits with up and down as well. So we also described that concave downward and concave upward are technically defined by how the slopes are changing. That is how f prime is changing. So if I put a series of dots on here and I were to look at the actual slopes, and I put the little arrow on them because we always go from left to right. Okay. Tell me what's happening to those slopes as we go from left to right. They are all increasing. Okay. The one to the right is a larger slope than the one to the left, even though they're negative. Okay. They can be larger. So when it's concave, when a function is concave up, if you analyze it, the slopes are always increasing. Vice versa, if I draw these points right here, and I draw the slopes for every one of on the function, when it's concave down, the slopes are always decreasing. Yes?
Is there like an easier way to find like the inflection?
It's...
Because like I never know like where to put it, I guess.
Yeah. The inflection points sometimes are mysterious to find, okay? But here's what we have to look at it. That's why I got a couple of graphs that we're going to point those out. So anytime you go from concave up to concave down, or from concave down to concave up, it's at that precise moment. There's one moment where the slopes go from either increasing to decreasing or decreasing to increasing. Now, in this particular graph, they are identified. And so this point is, these 3 points are called inflection points or points of inflection. Okay? Because that's where the function actually changes. The other key thing is that they are called points of inflection because they are actually points. Okay. Yesterday we took a look at an example, and I'll draw another one here. If you had a function that looked like this, okay, kind of like one of the secant or cosecant graphs with the u's, This is concave up, this is concave down. There is no point. This is an undefined value at x equals 0 here. Therefore, there's no point of inflection, even though the concavity changes. Okay? So it's, you can have concavity that changes, but not have a point of inflection.
If there was a continuous graph, then would there have to be?
There would have to be a point of inflection. Very good. Very good wording, too. Okay, so this is a quick visual. Let's take a look at a couple of other ones that I've got.
So,
Yes?
if there's like a hole in a spot, like that would be the point of inflection?
If this was an open circle right here, it would not be a point of inflection, because a point of inflection has to be defined. It has to be an actual point. An open circle means that it's an undefined point. Yeah.
There's no circle, but like the point was like 1 unit up, and then that be the point.
Yeah, that's a really good question. And she's saying that if this is an open circle, but maybe there's a dot right here, right? Would that be a point of inflection? And it would be an x value that's defined. That is where it changes concavity. So yes, that would qualify. It's an obscure case, but yes, that works. Very good. Okay, so this is just another picture. Everybody look at this picture. Does this picture make sense? It's got all three of the main words here. Concave up, you can look at it, concave down, and then the inflection points in between. Okay. Here's another graph. If you look at it, this is like, it's like a big hill that I would say you have to climb this hill, not slide down it, because we go from left to right. So if you were to have to climb this hill, okay, the moment where it would be the worst part of the climb is where the inflection point occurs. It's at this moment, as you're climbing up, that you're like, oh man, I just want to go back down. Okay, that's where the inflection point occurs. It's the steepest part of the graph. This is a really weird one. There's 2 points of inflection here. Okay. But there's cusps. So this is a function, but look carefully. As you go from left to right, you see how this concave down here? Okay, so it's concave down throughout this entire part. Then it converts over to concave up. That means that that's where there's an inflection point. Even though it's not a smooth curve like the other ones were. It's a different situation. Here, it goes from concave up to then, well, this should be a little bit more curved down to be good. Concave down, and then that would be another inflection point. Yeah, great. If it is a line, it's neither concave up nor concave down. Okay, yes?
Say like in the absolute value equation?
Yes.
Would it still be concave?
No. It's a great question. You think, well, wait a second. It does this, right? Isn't that concave up? And it's not, because the rate, remember how we compared it to f prime increasing or decreasing? F prime is staying the same throughout all of that. Okay? Yeah.
So at the point where that line, would that still be an inflection point?
This would be an inflection point as long as this is curving down.
And if it was a line, it would not be an inflection point?
It would not, because inflection points only occur when it changes from either concave up to concave down or vice versa. It can't go concave down to nothing. You guys are asking such good questions. I love it. Okay? Think about it at the beginning of the year when nobody said anything. Remember that? And you're just like, shh, don't say anything. Okay? You're supposed to say you're doing exactly what you should be doing. Okay, now, we're gonna have a little fun with, Desmos here, and I'm gonna show you an observation. Okay? So, I made a whole new thing, for you, and so, here is a function, okay? Here's a function, this is the f of x, okay? Can you identify where it's concave up and concave down? Can you identify the inflection point? Okay, so concave, just to summarize, concave up here to here, then this is where the point of inflection is, and then it's concave down throughout this entire interval. Match up? I've been trying to do the visual first as my approach here, so that's why we do the visual first. Okay, now watch this. I'm going to graph the second derivative. This is not the first derivative, but it's the derivative of the derivative. It's the second derivative. Okay? This is the second derivative of this function. So I'm going to scroll out so you can see that it actually does stop, because it's got an interval here. And I'm going to highlight that one. So, I'm going to show you a couple of these, and then we're going to make an observation about how we can actually look at the second derivative, and we can tell automatically if the function is concave up or concave down.
But why is the second derivative not like just goes the same?
Because we'll explain why. It's kind of cool how it all works out. So, here is the graph of the second derivative. So I just want you to watch something. From here to here, f of x was concave up. Okay? From here to here, the function is concave down. There's something to do with the green one, which is the second derivative, that you can look at and say, duh, of course it's concave up there, or concave down. Okay? Now we're not going to give it away just yet. I'm going to flip the sign here. So this was a negative, I'm going to change it to positive. Okay? And you're going to develop a theory in your head. Okay? So from here to here this time, the function is concave down. From here to here, the function is concave up. Okay? Developing a theory as to how this works.
Mr. Johnson, I did the wrong homework assignment that time, so.
That would be
All
why.
right.
I wasn't going to go there.
I was looking at this and I was like, wow, I missed a lot. I was like, I don't remember using the second derivative at all. Because I looked at Slater and he was like, use the second derivative. So I was like, okay, fine.
All right. We say problem solved.
Everyone's like,
I
all
do
right.
my homework. and I'm like,
Yeah, everyone's like, all right, whatever you say, Olivia.
Okay. This is the graph of the tangent function. Okay, I'm giving you a different function, and we're going to look at the concavity. Can you look at this tangent graph and tell me where it's concave up and concave down? You see the upward and the downward? Okay, now I'm going to graph the second derivative. And we're going to test the theory that you're developing in your mind. So, from here to here, the function is concave up. From here to here, the function is concave down. From here to here, the function is concave up. And from here to here, the function is concave down. Are you starting to develop a theory? Okay. Now, just to try to confirm your theory, I'm going to put a negative in front of here. Test your theory. right, let's do one more. Test your theory. Does your theory work? I'm going to put a negative on here. Test your theory. Okay. Talk to the person next to you. Share your theory.
What exactly are you trying to figure out? How to figure out where the point of the reflection is, or how to figure out when it's concave versus concave?
How to find whether or not it's second. How to find where the function is concave up or concave down by looking at the second derivative.
Oh, yeah.
Alright, so
I was so confused. I was like, okay, I was gonna I was like, I need to ask science if I'm in anything after I was like, and I was really curious, like, by the way, and I guess.
Okay. All right, let's put it on the board. Okay, in your notebook, let's put a summary of our knowledge up here so far. And I think we'll start at the beginning, where we say the following. F of x is concave up whenever f prime is, we're going back to yesterday's definition, concave up, it's increasing. This is actually the formal definition of what it means to be concave up. Second, f of x is concave down whenever f prime, angry eyebrows, is decreasing. Okay. That's what we looked at yesterday. Now we're going to institute the rule that you just formulated. So watch how I'm going to say this. F of x is concave up whenever f double prime is and how many agree with positive? Okay, excellent. And you guys figured that out by yourself by watching that. So the second derivative, wherever it's positive, we can tell that the function is concave up. Furthermore, f of x is concave down whenever f double prime is negative. And you can do as many graphs as you want to, and the concavity will always relate the second derivative whenever it's positive, the function is concave up, And wherever f double prime is negative, the function is concave down. Works every single time. Okay. Now, we should point out an inflection point. Inflection points occur whenever, we should say, at any point, at any point, and I'm stressing point because it has to be a point, where f double prime changes from negative to positive or vice versa. Another way to say it is where f of x changes from concave up to concave down, again, or vice versa. So where do inflection points occur? They occur when the function either goes from concave up to concave down, or when f double prime changes from negative to positive or positive to negative. Okay? So, I'm going to just give you a visual example. Okay? And I want you to copy this one down. This is the graph of f double prime. This is the graph of f double prime. If you just look at the graph of f double prime, you can tell where the function is concave up, concave down, and where it has inflection points. Okay? Let's identify this. Actually, you do it with a partner. Look at this picture. It's the graph of f double prime. I'm going to tell you that it's a continuous function. I'll say f is continuous. Okay? You tell me using the graph of f double prime, tell me where the function is concave up, down, and where there's inflection points. Do that right now with somebody else. All right, let's compare. So here's how I would do it. I'd say those 3 points are special. Okay, it's where the second derivative is equal to 0. Okay? But what I know here is that on this whole part right here, this interval from here to here, f is concave up. Okay? Now we're talking about f here, not the function. The second derivative is concave down, but we don't care about that. You know what I'm saying? This is the graph of the second derivative. So this is positive. So the function f is concave up on that interval. It's also concave up on this entire interval. Okay? So it's concave up here too, the function. We just find, hey, where is it positive? Now the last section right here, this is where the function is concave down. Okay, does that make sense?
Can you take anything out of f prime?
Yeah, I didn't want to confuse that yet, but there's a correlation between f and then f prime and then f prime to f double prime, which is kind of cool. So, because the second derivative is negative here, that means the function is concave down. Okay. Now, how many points of inflection are there? Good. There's only 2. One is here. The other one is here. Okay. This is not an inflection point at this value, even though it's equal to second derivative is equal to 0. But that's because the second derivative didn't change; it stayed positive. Even though it went from to 0 and back to positive, it never went negative. Okay. All right. Now we've been doing a total visual kind of big picture thing. Let's do an actual example now. Look at the front board. It's the same exact one as this one, just so you know, in case you copied that one down. So given f of x is equal to negative 3x to the 5th plus 5x to the 3rd, tell me about the concavity of that function. And we're walking. So now we're doing it analytically, see? And then we're going to test it using our graphing calculator to see if it all matches up. Okay, how do we find the intervals when f is concave up and concave down? And the points of inflection if we're given just the function? Step 1. What do you think? Yep. So step 1, find the second derivative. We're going to do that first. Because this is all based upon the second derivative. And let's make sure we agree. Okay. So step 1, find the second derivative. Okay. What are we going to do next? Yeah. We need to find the places where it's actually equal to 0 or undefined. Okay. So find where f double prime equals 0 or undefined, where there is no value. So we learned there's an easy way to do that. You just set the derivative, the second derivative equal to 0, and then you solve. So we're going to solve this equation for x. And it's going to find all the values of x where that's true. All right, I think a little factoring would help. So I'm going to pull out a negative 30x. Okay, negative 30x. That's going to give me 2x squared minus 1. No? 2x squared, I forgot the square. That gives me, correct. Everybody agree with that? Okay. So now it's in factored form, so we can go ahead and solve it. So from this puppy right here, we get x equals 0. If x were 0, bam, the equation would be 0. From this one, we got to do a little solving here. So 2x squared minus 1 equals 0. X squared equals a half. And then x equals plus or minus the square root of a half. Now, I'm going to put up a key word here. I'm going to say, therefore, watch this, there are 3 possible points of inflection. The key word here is possible. Just because the second derivative is equal to 0 does not automatically make it going to be a point of inflection. We saw that right back there. That third point, second derivative was equal to 0, but it didn't qualify. Okay, so make sure we circle what we got here. These are the magic points that we're going to use. Okay, step 3. Like we did in with the first derivative, we're going to make a chart. Okay, so we're going to make the chart. The all-important chart. And a chart is just a sideways t-table. And I'm going to make it long enough we get all of our points. So over here, we're dealing with x, but this time we're going to compute f double prime. Okay. So again, we do this in order from left to right, like it's a number line. It really helps out. So that means the first one over here is negative square root of a half. The middle one is 0. And then finally, positive square root of a half. Those are 3 x values that we already know the answer to the second derivative. And what are they? They're all 0. If we plug any one of those 3 into the second derivative, we're going to get 0. And the key is that if we use the factored form, it actually comes out to be a lot easier to do. Now here's the cool part. This is where the magic happens. If the concavity is going to change, it's only going to occur at these 3 values. Nowhere else on the whole function. This is the whole story right here. Okay, so let's just plug in some numbers to the left and to the right. Give me a number that's to the left of negative square root of 1 half. Negative 1 is a good one. Okay. Give me a number between negative square root of a half, and 0. I'm going to go easy here. Right? Because that's really close to 0. We know that this is, I'm not sure about that one. That's, not sure, but I know that this is between it. Okay. Then we fill in a number between these two. And then we're going to pick a number to the right. Okay, now we're going to take each of these x values and we're going to plug them into the derivative, or the second derivative. But I don't really want to use this one. I want to use this one. Okay, factored form might help out a little bit better. We'll see. Okay, if you plug a negative 1 in, I guess maybe this one might be easier for this one. If you plug a negative 1 in for x, what do you get for an answer? I got 30. Because this becomes positive 60 because of the negative, and that becomes negative 30. So it becomes a positive 60, or probably a positive 60, but the only thing that we care about is whether or not the second derivative is positive or negative. So we're going to put a plus sign here. Okay, next one, negative 0.01. This is negative 1/100th. Okay, what do we get for an answer when we plug that in? It's a little bit of a number sense thing. Watch this. I'm going to look at this section and we're going to look at this section. These two things are multiplied together. Since that number is negative, do you see that we're going to get a negative here times a negative? So this part right here is going to become positive. Okay? Now the question is, what happens here? 2x squared minus 1 means we have to square that number, multiply it by 2, and then take away 1 from it. Is that going to be positive or negative? It's going to be negative. Now, if you're unsure about it, then you use extreme values. Like this is negative 0.01. Why don't you make it negative 0.00001? If we square that, it doubles the number of zeros. And then multiply it by 2, which doesn't impact it that much. And then we take away 1 from it, it's going to be negative. Okay, so this is a negative. Keep going. This is a 0.1. What happens to the result? Well, this part is now positive because it's a negative times 0.01. So that's, pardon me, that's a negative now because it's a negative times a positive. And what happens when we do the same thing here? 2 times that 0.01 thing squared minus 1. It's going to be a negative. So negative times a negative is a positive. And the last one, that's a nice and easy one. If you plug a 1 in here, is the answer negative or positive? Negative. Okay, you get a negative 60 plus 30. So this is negative. This tells you everything you need to know now about how to find out where the function is concave up or concave down. This is exactly like the picture back there, but the picture is a visual, this is a chart. So look at, this is where the function is concave up, concave down, concave up, concave down. Are there any inflection points? Yes. Concavity changed here, here, and here. So there are 3 points of inflection. Now, step 4, just a second. Step 4, we're going to finish tomorrow, and that's our summary. And that's where we wrap it all up.
Since we know that those are the points of inflection, after we find one, can we just assume that the next one is negative, the next is positive?
Not always. Look back here. We went from positive to negative to positive. You know what I'm saying?
Yeah.
So it doesn't always alternate. In fact, it's possible to even do this. Okay? It's possible, it's just based upon the function. So, all right, remind me tomorrow that we got to finish with step 4. Okay.